Okay, so I have just kind of an outline of stuff to talk about today, but some of it involves looking at a couple of the handouts. Actually, we're going to look at the linear combination of vectors hand a little bit. We're not going to completely finish it. I'm going to skip some stuff so a little bit later. So we're actually going to even look at the third handout a little bit today, just because I'm trying to sort of follow the book. But let me remind you where we were. Right, so we were talking about linear combination of vectors, right? We were doing all this stuff with, you know, like if some vector we written as linear combination of others. I think what we sort of got to last Thursday was these three vectors here, and started thinking about what they actually span. And oh, you know what? I have some Mathematica code that I can show you a picture of this. So let me just download this and open this. Switch the share. Yeah, so actually, sorry, I didn't think about doing this. Go away. Okay, so here, let me make this bigger. Yeah, so let me just run some of these. So this is just a Mathematica is this visualization software, right? And or it's this mathematical software that you can actually download. I don't use it a ton in this class, but it's nice for visualizing some stuff. Sorry, I got to run all these commands first before I can. So I'm actually defining all those arrows in that. Silly. Defining all the arrows in this, all the vectors in this V1, V2, V3, and W. And actually I'm doing I. And so if you look at them all, so here they all are. I think I stretched I a little more to make it a little more obvious, but here, so the blue vectors are the V1, V2, V3 from the handout. And the gray vectors, the W, the -1, 1, 1, and then the red vector's I. But if you start like kind of dragging this around, you notice something, right? Like the blue one are not just three random vectors, right? They have a relationship to each other. Do you see that? They all, that's kind of what we were saying at the end of class last time. They do all live in the same plane. And moreover, W seems to live in the same plane also. It's weird how the arrows heads turn sometimes. Mathematics is a little strange. And then, oops, what did I just do? Sorry. And then the I vector, the red vector, is not in the plane. And so that ended up not being a linear combination, right? And actually, we even found the equation of the plane. And I think up here it's 2x minus 3y plus 5z, or 2x1 minus 3x2 plus 5xz, x3. I think that's what you guys found as that equation. When you Loewe reduced, right, this is sort of what you got on the bottom right. And in fact, this is the equation of the plane containing these vectors. And I is not in that plane. Does that make sense? Good. So yeah. Actually, let me just go to the board. Okay, so yeah, just to recap what I was saying, and you probably have this in your notes from last time, but we were just kind of right at the end of class. So so example of three vectors in 3D we had was this. So I'm just going to make that matrix right 4, 1, negative 1. What's the V2 vector? I can't really see from here. Someone read it to me. 2, 3, 1. And the last one? 1, 4, 2. Okay, and then we augmented that with a generic column, right? And then we row reduce. And the thing is, we end up with, if we go all the way down to reduced echelon form, and that's where you could get the equation of the plane, which was the 2b1 minus 3b2 plus 5b3. Something, oh, sorry, that's a 0 right there. By the way, you can check that each column satisfies this, right? Each column actually satisfies this equation. Like if you do 4, 1, negative 1, right? I think that works. If you do 2, 3, 1, 1, and if you do 1, 4, 2, like 2 minus 12 plus 10. Yeah, so all these vectors, this was sort of the V1, V2, and V3. V1, V2, V3. And this last equation says we need, for consistency, we need we need 2b1 minus 3b2 plus 5b3 to equal 0. And notice each of v1, v2, v3 check each of v1, v2, v3 satisfy this, and w, I guess. Satisfy this. I does not satisfy this, right? Because you just 1, 0, 0 definitely does not give you 0. And so that's explaining something. So, but I guess, so, okay, so that's kind of the whole, like, that's the picture. That's how we found it mathematically. It's kind of neat because if you think about it in multi, how would you find the plane containing 2 or 3 vectors? People remember? What was the multivariable way? If I gave you these 2 vectors and I said, find the plane containing these 2 vectors. Huh? I heard someone. Cross product. Was it Ali? Said that? Good, you're in my 1800 class, so that's good. You remember. Yeah, you would like cross product the 2 of the vectors to get a normal vector. And then normal vector would, yeah, so that's a different technique. This is another technique, but it's kind of nice. Like it just kind of works. So yeah, so what we would say is I want to define the span. And it's on the handout also. If you go to like page 3, it's page 3. Page 3 of the handout. Yeah, it's at the top of page 3 also, but I want to. So the span, given a set of vectors v1 through vn, the span, we write it like this: span of v1 through vn. By the way, this isn't Math 2020. You may not have taken reasoning yet. So just whenever we write a set, we use curly braces. Set just means a collection. Right, and so we just put curly braces around it to say we're like collecting something. So that is just the set of these n vectors. But the span is the set of all linear combinations of these vectors, where the C sub I are real numbers. Can I use this notation? This is real numbers. This is lives in vector is an element of this little epsilon looking thing. So what I'm saying is basically you just pick any coefficients. And so this is like the set of all possible linear combinations. So maybe I should say, like, in words, it's the set of all linear combinations of the given vectors. Handwriting is deteriorating. Yeah. Sorry, it lives in quotes or is an element of quotes. Sorry, yeah, no, this is terrible handwriting down here. That's just what this notation means. And I would like to get used to, you know, some notations like this. That's just, I guess I put it, oh, maybe I wrote it differently up there on the handout, where C1 through Cn range over all of R. Basically, you can pick them to be anything. This is, when you're writing on the board or on paper, mathematicians get lazy and like to use symbols for shorthands and stuff. Okay, so the set of all linear combinations of V1 through Vn. And so in particular, this example, so the example above, the span of V1, V2, and V3 is this plane in R2 plane in R3, three-dimensional space. Have I been using this notation too? Sorry, Rn for the n-dimensional, okay. I teach this in math reasoning back to back, and sometimes I forget what I said to do. So the plane in R3, notice it does go through the origin. I mean, that's gonna turn out to be important. Given by 2x minus 3y plus 5z equals 0. Or I could use the b's, or I could use x1, x2, x3. I'll just stick with x, y, and z for now. So the span of those two vectors is just a plane, right? Whereas versus something like the following, if you took the span of I, j, and k, right? If I take all possible linear combinations of I, j, and k, you're going to definitely get all of three-dimensional space, right? It's all of R3. So you can get different answers depending on the vectors, like if they're related to each other. You know, the fact here was that V1, V2, and V3 had some relationship to each other, which is why, like, they all lived in the same plane. So that's why it didn't span everything. Does that make sense? Okay. I guess what I want to think about then is what are the possible spans? Let me go back to my note outlines for a second so I remember what I wanted to do. Oh yeah, there's this idea of linear independence, which we will definitely come back to. It's not really until section 1.7 of the book or something. So yes, okay. So right. So I guess I want to think about a couple things. First off, kind of like what we were doing last time, where sorry, coffee necessity. Where we were looking at geometric relationships, but looked at geometry and then compared that to reduced echelon forms. One thing I'll say is, though, the geometry is different now because, like, when we had three equations and two variables, we had three lines in the plane. But that was like a 2x3 matrix, or well, that was like, yeah, the two columns, the two coefficient column, like a 2x3 matrix sort of, or rows by columns, 3x2 matrix, where, like, you know, the coefficients made a matrix and then we were reduced. But now if you're thinking about columns, you'd be thinking about two three-dimensional vectors. Instead of three lines in the plane, you'd be thinking about two vectors in 3D. So it's a different geometry, so you have to be cognizant of that. And something we're going to talk about a lot is like shifting perspectives. Like there's a row perspective, there's a column perspective. We're going to talk about this matrix transformation perspective in a few weeks or a week or so. So let's think about this. Let's think about the 2D case. So what are the possible spans of a set of vectors in 2D? So for example, you could have the span of like I said, I and j and k, or I and j. So let me just say 1, 0, 0, 1. Right, that's all of R2, right? That's the whole plane. We saw an example. The example we saw in the handout, the 2D example, was that the span of 3, 1, and 4, -3 all of R2, right? Because we sort of said we could find any vectors, linear combination of these two vectors. That was from earlier on the handout. This is page 1 of the handout. What else could we have? We could have, how about something like this? What if I have something like this? What's the span of that? I take all linear combinations of those vectors. I did the math right on those. Yeah. Yeah, do you agree? Yeah, it would be like everything is all multiples of the 3, 1 vector, right? So we could actually just say that this is really the span of just the 3, 1 vector, because these are all multiples. If this is v, then this is 2v, -3v, and 50v. So it's really just the span of that. And that's a line through the origin. Okay, so one possibility we found is all of R2. Another possibility we found is a line through the origin. You probably believe I could change the numbers to make any line through the origin. And here's a, actually, you know what I should have thrown into this set? Or I'll even be silly and throw the 0 vector in. Doesn't change anything, right? Any multiple of the 0 vector is the 0 vector, so that doesn't really change anything in linear combinations. So here's another one. What is that? What's the span of the 0 vector? Yeah. Just the origin, right? There's no way to get away from the origin if you just have the 0 vector. So that is just the origin. Right. Some people would write this as like 0 with an arrow over it. Okay. And so that's also a possibility. So notice this is a 2D span, this is a 1-dimensional span, and this is a 0-dimensional span. 0D. Right? Yeah. Yeah, so that's interesting, right? So like if we had a line not through the origin, I guess the question is like if you just think about all possibilities of vectors and what you would do. Like one thing you could say about this is that this is 0 times v. And in the definition of span, the C's could be 0. And if all the C's are 0, what do you get? Like all those C's up here. If these are all zeros, you get the origin, right? So the 0 vector is in, the origin is in every span. So every span has to pass to the origin. It's a good question. Yeah, it's an important point. Like, note, C1 equals C2 equals, or just like, they'll just say 0 V1 plus 0 V2 dot 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 plus 0 Vn, which is a 0 vector, is in the span of V1 through Vn. So that means every possible span is something through the origin, right? And they're all, well, okay, so that was a line. Could you get something curvy? Could I get like a sine wave through the origin as a span? Once I have a vector in my span, what else do I have? Like if V is in my span, tell me some other vectors that are in my span. Yeah. 2V, 3V, 4V, 5V. So as soon as a point is, like if you're just like in the plane, and as soon as a point is in your span, I mean a vector is in your span, then do you agree the entire line, because you can scale the vector by anything? So the entire line is in, so everything is in the span. Oh, you know what? I really should be assigning you those 3 Blue 1 Brown videos, because he has beautiful pictures of some of this stuff. But yeah, so once V1, if V1 is in the span, or sorry, if V, or let me just say if W, there's note 1, note 2, if W is in the span of a bunch of vectors, again, there's that element of thing. Then so is CW for every C, for every scalar C. So the whole line, i.e. the line through, the line containing W is in the span. In the span. Right, so it's kind of linear in that sense that like we can't get curvy things because we could get off curvy things by scaling. Maybe that's silly, but like I'm saying, if you had something like this, well, that's not sine, but that's something else, then that would mean this vector's in the span, which would really mean this whole line is in the span, right? And every line. So actually, if you had a bunch of vectors lying on a sine wave, then in fact the span would have to be all of R2, because you can scale and get off that sine wave. So spans are inherently like linear objects. Are, I'll just say linear in quotes because I'm not defining that super precisely, but let's think about 3D, for example. What do you think the possibilities are in 3D for spans? We've seen a couple examples already. Yeah. The plane. Oh, like a plane, right. So this is all of the, and now plane through the origin. Yeah, exactly, right. So yeah, so in 3D, it's that, those are the possibilities for spans, right? So and by the way, these objects, I should tell you the name, it's going to come up later anyways, I might as well tell you now. These sort of like linear things through the origin, like lines and planes through the origin, are called subspaces. We're going to use the word subspace for those. So spans in 3D. You have the origin, lines to the origin. Right, if you just took the span of one vector, one 3D vector, it would be just a line containing that vector. Planes to the origin, like that example that we started class with. And all of R3. And all of R3. Okay, right, so those are the possible subspaces. They're always these like linear objects to the origin. That's what I mean by linear. It's like lines or planes or linear objects, right? Linear meaning nothing curvy. Okay, and then one thing worth, sorry, any questions? Yeah, I think I saw you do like this. Questions are good. So in fact, we're sort of answering some of these questions on page 2 of this handout after we got, like, suppose you have 3 vectors in R3. Oh, actually, so this is interesting. Well, so here, if a given vector set of vectors doesn't span the whole plane, what kind of geometric objects can it create? So that's like, we said a line for the origin. It is interesting to think about the reduced echelon form. So, right, if we have, I want to connect to the echelon forms. Like I said, similar to what we did with the row perspective of equations. Let's do the 2D case first. So if I have, you know, the span of 3, 1, 4, -2, 1, 7, 10, 10. Here, I'll throw in the 0. No, it's just, okay, 10, 10. Well, what I'm saying is let's take the matrix where these are the columns, right? And I claim you sort of already know how this is going to row reduce. How is this going to row reduce? And that's what I'm saying. Before we would have thought this as two objects in 3 or 4 dimensional space or something. Instead, we're thinking about 4 objects in 2-dimensional space. How would this row reduce? How many pivots would we get? You're answering everything. Someone else. Appreciate it. Try to hear from other people. Be bold. Boldness is good. Yeah, you're 2. Right, you definitely would end up with 2 pivots because these are definitely not all on the same line, right? So it's something like they point different directions. And so when you row reduce, I think you'd end up with this and then, right? And so in fact, the span is all of R2. And we get 2 pivots. What if we had the span of like what we had up there, like 3, 1, 6, 2, 0, 0, 150, 50. So now we'd make this matrix 3, 1, 6, 2, 0, 0. I guess I'm allowing 0 columns now. I sort of saying when we were thinking about systems linear equations, having 0 columns is kind of stupid because it just meant the variable wasn't involved at all. So what would this row reduce to? How many pivots would there be? Yeah, just 1, right? Yeah, like the first row is 3 times the second row. In fact, you can see, you can eyeball completely how it would, I don't even need to use the asterisks. Right, I don't know, 50. I can just swap the rows and subtract 3 times the second from the first. 3 times the first one, the second order. So that's one pivot. So the span is a line through the origin. And there's one pivot. Can you guess what I'm getting at here? Yeah. Sure, you mean like the equation of the line?
Like we figure that out just from by looking at the original vectors,
in the math? Well, if I augmented again with the generic column, right, like a B1, B2, then we switch and subtract, I think we would get B2 and then B1 minus 3B2. And that has to equal 0. So that's x equals 3y, right? That's a good point. Like 3b2 equals 0, x minus 3y equals 0, x equals 3y. And if you think about that, that's true for all of these, right? The x coordinate is 3 times the y coordinate in each one. You get a question? Exactly, yeah, like dimensions match, right? Like line is 1-dimensional, 1 pivot. Plane is 2-dimensional, 2 pivots. If we just have 0 vector, that matrix has no pivots. The matrix 0, 0 has no pivots, right? You can even say span of 0, 0 is the origin, and 0, 0 doesn't really reduce to anything, doesn't change. No pivots, 0 pivots. So good. Note, Sydney? Okay, Sydney noticed that like number of pivots matches the number of dimensions of this span. So the dimension of the span equals the number of pivots. And that's very true. It's like, that's always going to be true, yeah. That's cool. So yeah, and in each case, you can find the reduced echelon form, the coefficient matrix. I guess I could have had some slightly different things here. I could have had, I'm just thinking about how I can alter this to change things slightly. Like this one, if I just wanted to alter this slightly, just to see different things that could happen. Alter slightly. If I had 3, 1, 6, 2, 1, 7, 10, 10. This first, second column is a multiple of the first, right? So that would actually row reduce to 1, 0, star 0, 0, 1, asterisk, asterisk, like that. Because when we subtract and clear out, these would both disappear. So we get 2 0. So it still has 2 pivots. It's just the second pivot doesn't appear until the third column. So basically, as long as any of the 2 of the vectors don't point in the same direction, you're going to get 2 pivots and you're going to span all of R2. Okay. So this is also 2 pivots. I mean, it's sort of a thing that like once you have the 2 vectors pointing in different directions, the rest of the vectors are sort of redundant, which we'll talk about, like you don't need them for the span. But here, the first 2 vectors are not, they're not like pointing in different directions, so you need the third vector. That's gonna come up later, so I'm just gonna get it on your head now. Good. Let's see, let's just look at these questions and see if we'd actually answered them. I guess I did, the 14, 15, 16 is about the redundancy, about the linear independence stuff, so I'm not gonna, I think we basically answered 11, 12, 13. Yeah, if you do have 3 vectors in R3 that generate all of R3, what's the, I mean, I guess I was doing 2D examples, but we could do 3D examples also, right? So, and maybe I'll just go ahead and write this, like if we're gonna actually a lot of times I'm going to write matrices in a sort of abstract way where the columns are vectors. So I'm not going to actually write the columns like wait, I just erase the same thing. No. Okay. Sometimes I switch the boards twice and then erase the board. I just erased them. Not realizing I don't want to do that. These people are catching up. I was always a slow note taker. So. Just 3D example, like if the span, let's just say we actually had 3 vectors equals all of R3, then the matrix whose columns are V1, V2, V3. So this is what I mean. I mean, this is the matrix whose columns are like that. So the columns are that. Then what would that row reduce to? How many pivots should we get? 3. And what does a 3 by 3 matrix with 3 pivots look like? Yeah, 1, 0, 0. Because like, yeah, basically this is the simplest case of a row reduce of an echelon form, right? Because that's when you're solving, you get a unique solution. If I had an augmented column, I could read off the answers immediately, right? So that row reduces to the identity. Oh, there's a name for this matrix. This is a special matrix because it comes up when you have like things are nice, like situations where it's nice, where the vectors do all point. The 3 vectors aren't coplanar. So if they're not coplanar, they point in 3 different directions, and that means you can generate all of R3 in the span. And there's a name for this. It's called the identity matrix. It's the first time we encounter something, I'll try to give you the terminology so that when we see it again later, I'll have at least said it once. There's a name for that. That's if you happen to have 3 vectors in 3 dimensions, right? I mean, we could have 17 vectors in 3 dimensions, and we'd have a 3-row, 17-column matrix. Or we could just have 2 vectors in 3 dimensions, and we'd have a 3-row, 2-column matrix. Okay. Makes sense. All right. So we've answered this. We'll come back to those. We define span. Here's the subspaces. We're going to come to subspaces too. I already mentioned that these things are called subspaces. I haven't even written it on the board, but again, we'll come back to the idea of subspaces, but it's kind of an interesting idea. And then we'll come back to the idea of bases. Okay, so I think actually I want to go ahead and look at the next. Yeah, I guess hopefully we'll get to group work. So where's the next handout? Yeah, here it is. Let me share screen. Okay, so I really want to start using matrices more and more. I mean, we already sort of are there, right? One thing that, before we even do that, I just realized as I was speaking, I don't think we said this explicitly together, that this for example, is called, stop my share for a second, oops. This, for example, is called a 2 by 4 matrix because it's 2 rows and 4 columns. Okay, so we call an m by n matrix an m by n matrix means m rows, n columns. And we always use m and n, which is always dangerous because they sound alike. Yeah, so we're going to talk about matrices a lot, and so I'm going to refer to like it's a 2x3 matrix, it's a 3x2 matrix, it's a 7x14 matrix, you know, stuff like that. So I guess there was also the notational thing, which I don't think we ever talked about. The idea that we use the double subscripts. I think that's on, you know, an earlier handout. But that we write like say I had a 3x4 matrix, then I would write it like this, like a generic one. Because you start to run out of letters. If you use letters, different letters, you start to run out. If I have a 1,000 by 1,000 matrix, I'm going to run out of different letters for each inch if I want to write in general 1,000 by 1,000. So instead, you use this double subscript notation that is like this. Oops. 2, 3, A, 2, 4. You can probably guess the pattern here. So this is 3x4. And what is A sub ij? It's the entry in, like A sub 2, 3 is the entry in what row and what column? Let me just say it. Second row, third column. Thank you. Sometimes just say stuff. I'm just looking for the quick response. Second row, third column. So this is the entry in the ith row and the jth column. So if I have a general n by n matrix, I could, there's an annoying thing with trying to write dot dot dots to like say I have like a 100 by 100 matrix and I want to like, you have some dot dot dots because you don't want to write all 10,000 entries. But at the end, you could say I have A sub mn. It's an m by n matrix. Okay, so just to make sure we're on the same page with like notational stuff. These are called double subscripts. It's a little weird if you get to more than 10, although you never really do in practice, but you might want to put a comma between the subscripts. Otherwise it starts to get confusing. Okay. So now let's look at this handout. Because there's a slightly different way to look at things. We're going to start talking about matrix times a vector, what it means to do a matrix times a vector. Let's just sort of read this together. So, right, I mentioned we denote n-dimensional space by R sub n. Here's a system, just kind of a random system. I'm claiming 1, 0, 2, -1 is a solution. Check that. Somebody. You guys check the first equation. You guys check the second equation. You guys check the third equation. See, I claim 1, 0, 2, -1. Works. Oh, like this thing right here? Yeah, well, it's, I mean, up here at the top, it's like, here, x1 equals 1. The claim is that that's a solution to the system. So check it quickly for me. You should always check these sort of things. Once you get an answer to a system of equations, you should check. If it actually works, you know. Does it work? All nod. Okay. So, so yeah, we can write that. Let's talk about matrix vector notation. I'm going to basically be saying the things that are on the screen, but so we have matrix, or maybe I'll just say like AX equals B notation. Actually, as a silly example, first silly example, What if we have one equation and one variable? One linear equation and one variable. That's basically AX equals B like that, right? So I'm saying this is kind of generalizing to higher dimensions. We're going to generalize this to like look like that, basically. Okay, so this is a 3x4 example, I guess. So the coefficient matrix at least is 3x4. So 3x4 example. Let's go ahead and write it down. It's always good practice to write things down. So 2x1 minus. Should really be having just someone read it to me, I guess, but someone read me the second line. x1 plus 3x3 plus x4 equals 6. And then the third line, 2x1 minus 3x2. Three. Okay. Okay, so we could definitely change this into like augmented matrix, no problem, right? I think that's what you would do. Let me go ahead and do that. Wait, did I stop the screen share? Yes. Paranoid about that. Okay, so we have this sort of augmented matrix form. And I'm not talking about the whole solution, I'm just talking about one specific solution being those numbers given. In fact, this has more variables and equations. So there's probably more solutions. There should be a free variable, right? Because you have at most 3 pivots. So that the augmented matrix is 2, 1, 2, -3, 0, -3. Trying column by column, right? -1, 3, -1, 2, 1, 3, augmented with -2, 6, -3. And we can reduce and solve, but and maybe we will at some point. But my point is, it looks like, so it turns out, what was it? 1, 0, 2, -1. x1 equals 1, x2 equals 0, x3 is 2, x4 is -1 is a solution. And I guess what I was saying is, yeah, write that as a vector itself, like it's a tuple, right? So let's think of that as a vector. We can think of this as I call it x naught. Yeah, it's like specific solution. 1, 0, 2, -1, living in 4-dimensional space. And it's almost like we've separated out, like we have this whole thing here, which we could call our coefficient matrix. A. We have this, which is a vector itself, B, in R3, right? And we sort of separated out everything where the solution now. And so now we have these 3 objects. We have this A, we have this B, and we have this x naught. And this is a solution, and it's linear, and it's supposed to be an analog of like that 1-by-1 case up there. So it just means we tend to write A times x equals B. And that's actually a way we use to define matrix, like a matrix times a vector, is we just define it this way. So by analogy with the 1-by-1 case, let's write AX naught equals B and use that to define what we mean by matrix times vector. that to define a matrix times column vector. Okay, so this ends up being like a definition of like matrix times a vector, which maybe you've seen before, but it's kind of like this is where it comes from. If I scroll down more, just on the handout, yeah, we have a general X. Right, I could write a general X here, which is like X1, X, representing the variables. Because that's a solution, this is a solution versus like the sort of general equation, we would write AX equals B. So this is like for the solution, or the general would be AX equals B, where this is a variable vector. Okay. And so what we do, if you think about this, so let's see. So I guess what I mean, if we write this out, I'm just going to kind of write out what we have there, i.e. A times X is this matrix. First column 2, 1, 2, second column -3, 0, -3. Third column -1, 3, -1. Fourth column 2, 1, 3. Times this column vector. And this looks a little funky. Let me just do the generic one, the general one first. Right, we're going to multiply those, and the product is supposed to be the left-hand side of that system of equations. So we're going to get 2x1 minus 3x2 minus x3 plus 2x4. So now this is a matrix, but it's actually a vector because this is one number, and this is going to be a number for any specific x's we plug in. Right? So we get x1 plus 0. Let me write it out. 1x1 plus 0x2 plus 3x3 plus 1x4. 2x1 minus 3x2 minus 1x3 plus 3x4. So like that, right? That's the definition of what matrix times vector is. And if we plugged in the numbers 1, 0, 2, -1 to here and to here, we should get the -2, 6, -3, right? I guess I wrote that there. Now the question is, how do we sort of remember, right? Like, how do you, there's two different ways to remember this. And one is like the easy way that I always remember. That's what I was just doing just now when I was writing out the product. Do you want to talk about the, so if, okay, here's the thing. If you think about it, actually, maybe I will do the, sorry, I know it's a lot of writing, but maybe I'll do, I think when you do math, you just have to get used to like saying that you're going to write a lot. I'm actually going to try to illustrate this with this example, 1, 0, 2, -1. But I'm going to actually write out what happens when you plug this in. So we get 2 times 1 plus -3 times 0 plus -1 times 2 plus 2 times -1. Right, I'm just plugging it in there. But I'm not simplifying anything. I'm just sort of doing a question. Hopefully I did that right. I'm just plugging in the values of x1, x2, x3, x4. Here we get 1 times 1 plus 0 times 0 plus 3 times 2 plus 1 times -1. Yeah, I mean, each of you did one of these computations, and so you probably got. I know I'm belaboring this a lot, but I think once you see it, it'll be easy to remember. I thought Jack was so bored he was leaving when I heard the zipping of the. So this is just plugging in, right? Plugging in x1. We're just plugging in x1 equals 1, x2 equals 0, x3 equals 2, and x4 equals -1. Okay, but there's a way to remember this and see this. If you sort of take it away, if you just want to think about matrix times vector, what actually creates this first row? I mean, okay, so this ends up equaling -2, 6, -3, right? Okay, but that's fine. But I don't want to care about that. What I want to care about is what numbers actually go into creating this number? What numbers from here? Coefficient, but which ones? Is it all of them? Do all these numbers go into this first row? Just the first row here goes into the first row here, and then the column goes into the first row here. So it's something to do with this row and this column. Can you tell what I'm doing with that row and that column to create that? What am I doing? And then you add them all together, right? That's a familiar vector construction to you, maybe. What is it? Somebody say it. We did it in 1800. It's the way we combine vectors in 1800. Yeah, dot product. It's a dot. It looks like a dot product, right? And in fact, that's the way I remember matrix times vector is like you dot the first row with the column. Yeah.
We've been thinking of the columns as vectors when we've been
That is true. I see what you're saying. This is just like a computational shortcut in our heads for how to think of how to multiply matrix times vector. There is a way that uses the columns too, which I'm going to show you in a minute, which is actually the better conceptual way. But just as a computational shortcut, you can think of this as we could, sort of a computational, I don't know, mnemonic or something. I don't know if it counts as a mnemonic, like officially, but it's basically like row 1, row 2. But you're right, I'm thinking of the rows as vectors now, which there will be times in this class where we do think of the rows as vectors. Row 3 times this column, and these are all vectors, I guess. And then that's going to equal like row 1 dot the column vector. And this is row 2 dotted with the column, right? So I'm just saying, if you want to, like when I was just doing this, actually, like when I was writing this down, I was literally just doing that in my head. I was just dotting. So I didn't have to even remember what the equations were. Once I had it written like that, I could just sort of dot in my head. So it's like dot product. Okay, so that's one way to do it. Yeah.
The one question I'm still about. So like with this thing, we have 3 equations with 4 variables. So we should have a general equation that can express all solutions with 3 variables. So could you use this method of dot product to find that general equation instead of finding
Like if I wanted to actually solve x1, x2, x3, x4,
yeah,
like the general solution?
yeah.
Well, actually, so in order to find the solution, we really still need to like row reduce this, and you have a free variable. We'll talk about, actually, that's something we're going to talk about soon, which is like, how do you actually solve this generally and write down a general solution as a 4-dimensional vector? But you're right, there's some weird stuff going on here, which is we have like a 3 by 4 matrix we have a 4-dimensional vector. We multiply it by, and we get a 3-dimensional vector as a result. It's already a little bit weird, right? In fact, maybe I should just write that down. Like, we have an m by n matrix times an n-dimensional vector, and we get an m-dimensional vector. So this is something that takes time to get used to. That like, it even doesn't even look quite right to write like this times this looks strange. But if you think about it, it's really number of columns here has to match number of entries here in order to get that kind of expression up there. So that's why you get this something that looks kind of strange, because it's really the number of columns has to equal the number of columns of the matrix has to equal the number of rows of the vector, number of entries of the vector. Does that make sense? Okay. So that's just like computationally how I think about it when I'm doing actually matrix times vector. And we're going to do matrix times matrix, which is going to be something sort of similar at some point soon. But yeah, question. No, it's good. The order of matrix times vector?
Yeah, like you swapped it so that the
Yeah, so right, because you're saying dot product is commutative, so why not put that first, put the column first? Yeah, it's interesting. It turns out this is more about having to do with like matrix multiplication than matrix times vector, but you're right. This is sort of multiplying a matrix on the right by a column vector. There is a similar thing, which is multiplying a matrix on the left by a row vector. Let me think about how to explain this for a second. So I can't just put the vector in front of the matrix because, I mean, again, this is convention, but it's like we tend to write it this way as matrix times vector. There's something called the transpose of a matrix where you swap rows and columns. So I could take that 3x4 matrix up there and make it a 4x3 matrix by like taking the 3 rows and making them the 3 columns. And what we sort of have there, yeah, I mean, let me just write this, and it's something we're thinking about and coming back to you later. It's good. You're anticipating stuff that we're gonna do later and asking good questions about like what kind of the constraints are, the conventions are and stuff. So we could have written something like this. So now if I change the rows and columns, so now the first row becomes the first column. The second row becomes the second column. Third row becomes the third column. And now, again, it's sort of like dotting. But now we're dotting this with each of these, right? And we would get -2, 6, -3 like this. So it is possible to do like row vector times a matrix. But because this isn't really natural from the perspective of the system of equations, I think we don't tend to write it that way. But this is actually called A with a superscript T, which is A transpose. In fact, these are all considered transposes. This is like X naught transpose. Because if we switch rows and columns, we make a column vector into a row vector. And this is B transpose. But there is a thing that people start to write matrix. I mean, it's worth talking about here because there's actually a way people write dot product, which is differently than you're used to, which is like some people write, or not some people, we can write, I'll just say we can rewrite dot product as let's just say we have like x, which is x1, x2, x3, and y, which is y1, y2, y3. Then x dot y is just, like we said, x dot y is x1, y1 plus x2, y2 plus x3, y3, right? But you could also think of this as, if I take x transpose, turn it into a row, and multiply it by y. So notice, so yeah, the transpose is swap rows and columns. It's sort of like flipping the matrix along the diagonal. Right, it's kind of like flipping the matrix like that, or flipping a vector. So notice x transpose y is like this. We would write it. So we tend to think of vectors as column vectors, and if we want to write a row vector, we write column vector transpose. And that really is, by definition, what we just sort of said, right? We do x1 times y1 plus x2 times y2 plus x3 times y3. And that is x dot y. So it turns out that, like if you go on in math, a lot of times you'll just see the dot product written as that instead of x dot y. It's kind of a weird thing you have to get used to. And even in our book, it does it later. It's like, you have two vectors, which are column vectors, then one way to write their dot product is x transpose y. Again, this is stuff that's going to come up later, but it might as well. It's like, I like the idea of putting stuff in your head and then coming back to it. Good. Okay. Now the other thing which you brought up, which is, wait, what is your name? Sorry, Zephyr. Oh, you're Zephyr. Okay. Zephyr is saying is that it's a little bit unnatural what we're doing, especially it doesn't really fit the whole like. I mean, it does sort of fit the coefficients. If you think of the row perspective of these each row being coefficients of an equation. But what about in terms of the columns? And this actually has more conceptual weight to it, and it ends up being a way we're going to think about this quite a lot. Yeah, okay. I don't know if maybe I should erase that, but okay. There's also a column way to see a times x. So let me go back up to this system. And then reinterpret this solution, right? Like, let me just see here. I guess I have it. I don't want to rewrite all of this, but let me just pull this down for a second and say, notice this right here with these plus signs. The plus signs are there. You can imagine breaking this up into 4 vectors over the plus signs. And actually even pulling out the coefficient. The thing that's similar, like 0, 0, 0 is here. So maybe I will write that. This is going to be, okay. Like I said, you have to be, I was thinking about like Rafael Nadal who tries harder at tennis than anybody does anything on the planet. It seems like he's like the most intense. And he sometimes in interviews, he talks about how you have to be willing to suffer. And so he like just trains and trains and trains. He's willing to like suffer. He plays these 6-hour matches where he's like willing to suffer to be able to like, yeah. With math, I think you have to be willing to write stuff out over and over again. And that's like a little bit of the suffering. A lot of the suffering is just psychological of like feeling stupid. Math makes everyone feel stupid. But there's also the physical, like you just have to get used to like, I'm gonna write stuff out over and over again until it's almost embedded in my hand and I can do the math with my hand. So I just want to rewrite this AX naught. I'm going to copy this from above. To 1 positive 3 times 1, 0, 2, negative 1. Oh, okay. Okay, so this we said is 2 times 1. I'm also going to do it column. Well, okay, I'll just do it this. Negative 3 times 0. Negative 1 times 2. 2 times negative 1. That was the first row, right? And then similarly, okay, so the second and third row, 1 times 1 plus 0 times 0 plus 3 times 2. I'm really just doing the dot product in my head. Nope, yeah. Right? Now, what I want to say is we can break this up into 4 vectors. So 2 times 1, 1 times 1, 2 times 1, plus negative 3 times 0, 0 times 0, negative 3 times 0, plus negative 1 times 2, 3 times 2, plus 2 times negative 1. And now what I want to do is actually the number that's the same in all 3. I can pull that out as a coefficient, as a scalar multiple, right? So I can actually write this as 1 times the vector 2, 1, 2, plus 0 times the vector negative 3, 0, negative 3, plus 2 times the vector negative 1, 3, negative 1, plus negative 1 times the vector 2, 1, 3. And now this is a linear combination of the columns of A. You see that? Right, these are the 4 columns of A. And these numbers right here are the coefficients in front of each column. Does that make sense? So that's another way to define what this is you're actually, and it's a thing you could even rewrite. I mean, that's kind of how we rewrote systems in terms of linear combinations of vectors, right? I could do it up there too. I could sort of break that up into like the system of equations at the very beginning of this handout. I could break it up into 4 columns with the x1s, the x2s, x3s, x4s, and pull out the x1, x2, x3, x4, and make those scalars in front. And so this is really another way to think about matrix times vector, and it's actually conceptually a more interesting way, which is that, in other words, we're using the numbers in the vector x as weights. We can think of these as weights on the columns. Like, I haven't said it before with linear combinations, but you can think of the C, the scalar coefficients in front of each vector as weights on the vector, like if you're trying to do like a weighted combination of some things. So, okay, so let me just write that down. So after all that pain, by the way, my version of suffering is clearly very light compared to Nadal's version of suffering. I'm a total wimp. Suffering to me is writing something down more than once. It's not a pretty lame version of definition of suffering. Okay. Yeah, so in other words, we can think of the entries, think of A times X as a linear combination of the columns of X of the columns of X, of A, sorry, of A, where the entries in X are the weights on the columns. Are the weights, or maybe I just want to say scaling factors on the columns of A. Of, well, suffering versus not suffering. I need to not do 2 entire lectures in a row because my hand starts to cramp up. Right? Need to do more group work interspersed. Here's actually the weights. So what I'm saying here is that, like, again, if I do it sort of this way, where I think of the columns as V1, V2, V3, V4, I mean, I'm saying A times X. You write A that way, times X1, X2, X3, X4, we can think of this as X1, V1 plus X2, V2 plus X3, V3 plus X4, V4, right? And I'll admit, when I compute matrix times vector, I usually do it that way, but conceptually, this is gonna be much more important because this tells us something. And a lot of times we're going to try to like give arguments for why certain things are true. It's going to depend on this interpretation. Okay. Yes, I said this. Is it 1 o'clock? Oh my God. We're out of time. 1:05, right? Somehow I thought we had like half an hour left. What am I doing? Okay. So yeah, that's this last bullet point here on the outline. And then, so I guess what we should do, well, so like I was gonna have you guys work on, I mean, we can sort of answer some of these questions now, or you could, you know, I was gonna say make up like 2x2 versions of this just to, we did that one 4x3. Right, we sort of talked a little bit about this, like the matrix has m rows and n columns. Then the number of entries in X has to match the number of columns. And you can see here, you can actually see that the result, whatever the column vector lives in, like this is a vector in say 3 dimensions, then the product is also going to be a column vector in the same number of dimensions because it's just a linear combination of the columns. So if V1 is in R7, if the VIs are in like R7, say 7-dimensional space, then AX is also in 7-dimensional space because it's just a linear combination of the columns. Okay, so really what we have is we have M, I mean, I guess I wrote that down here, like M by N matrix times N-dimensional vector equals N-dimensional vector. M by N here means M is the number of rows. Number of rows is the number of entries in each vector. Hopefully that all kind of goes together. Okay. So what we'll start with next time, and I'll just have you guys work on this, is these homogeneous systems where you put all zeros after the equal sign, kind of like that chemistry example that we did. It turns out that if you want to solve a system in general, it's nice to solve the homogeneous version. Like this is the same system as this one, but I should have been sharing the screen the whole time. Sorry. This system is the same coefficients as this system, but we just made all the entries after the equal sign 0. And it's going to turn out that if you want to solve this in general, it's nice to solve what's called the homogeneous version, where you just make all the things 0 first. And that tells us something about the solution. So we're going to do that on Thursday. And let's call it a day because my hand's about to fall off. All right, thanks guys. I have office hours this afternoon.